So let's jump into the final section of this module, 2.4. This is talking about correlation. And so we just got done doing 2.3, which was creating this line, right? Like this line of best fit. And the question that we left you with was, how good of a fit is it? Does that line fit our data really well or really poorly? How do you determine? Could we boil it down to a single number and say this number shows how well the line fits our data? And we can do that. And that is called correlation. Okay. So here are some examples of correlations. You could have a moderate positive correlation. So a moderate positive correlation would look something like this. And you can see each point is, it's pretty far away from that line, right? And you'd have some pretty big areas of squares if you were to make this, okay? So that would be a moderate positive correlation. This would be a strong positive correlation. Again, the lines are, or the points are a little bit closer to the line. And then this would be a perfect positive correlation where a line perfectly fits the data. This does not occur in nature at all. Like you'll never have a perfect positive correlation, okay? But you could, I don't know, if you plot points, maybe you could create something that's pretty close. Okay, so then we have negative correlations. So these are correlations that maybe look like this. And a negative correlation is not bad. It doesn't mean that this is a bad correlation. It just means that the slope of a line is negative. So a positive correlation has a positive slope, right? The line goes up as you travel left to right. A negative correlation is a line that goes down as you go left to right, okay? And so that's what a negative, it's not that it's good or bad, it's just a different slope of line. That's all the differences, okay? No correlation just means the points are scattered everywhere, right? Like if you try to fit a line that goes through these points, like there's virtually no correlation. The points are just all over, okay? And then probably the most interesting ones, which we will not talk about in this class, are non-linear correlations. So these are correlations maybe that are parabolic, like a parabola. And their equation would be something like ax squared plus bx plus c, right? Remember parabolas maybe from algebra 2 or something like that, quadratic equations, factor it and find the zeros using complete the square. We're not going to do any of that stuff. We're just going to say these are nice, but we're not going to play with them. They're sort of exotic creatures in the math world, right? And there's different types of nonlinear correlations that you could do. You could do a polynomial, a binomial, exponential, logarithmic, sinusoidal. So if you take a look at the sunspots that are on as the sun rotates, it creates regions that are cooler. They get dark. It's called a sunspot. Sunspots, if you track how many there are, they have a graph that looks something like this. And if you count the number of sunspots, you have something called the sinusoidal model. And the distance from one peak to the other peak is about 11 years. So sunspots have this 11-year cycle and it's sinusoidal. And you can model it with a sine curve. It's pretty cool. If you look at predator-prey populations, if you have a herd of deer and some wolves, you go out to Yellowstone and look at the wolf population, you'll notice that predator-prey populations are sinusoidal, right? As the number of deer goes up, they feed the wolves. So the number of wolves goes up. If the number of wolves goes up, then the deer population goes down because they're eating the deer. But then now the wolves start starving because there's fewer deer. So as the deer go up, the wolf goes up. As the deer goes down, the wolf goes down. And there's a sinusoidal pattern to this. Predator-prey populations are sinusoidal. So there's all kinds of really cool models we could use to fit data. But we're just going to use boring lines, y equals mx plus b, ho hum, okay? So, but actually the mathematics is a little bit easier with the linear stuff. So there you go. Okay, so we're looking at linear correlation, specifically fitting a line to the correlation. And so how well does the line fit the data? We have a variable for this. It is called R. And remember back in the table where we had SSX, SSY, and SSXY, they show up here again. And here they are for our calculation of R. So you take SSX which was the sum of the squares of the x term, or the product, sorry, this is SSXY, the sum of the squares of the product of the residuals, and you divide that by the square root of SSX and SSY. These are three things that we've seen before: SSXY, SSX, and SSY. So you take those numbers from that table, which we're going to do in about 30 seconds, plug them into this, and that will create R. That is what's called your correlation coefficient. Okay. Some things about R. What do you need to know about R? R bounces between 0 and 1. So if we put it on a number line, you'd have like negative 1 and 1. What am I saying? 0 and 1. If we put it on a number line, let's say you had -1 there and +1 here, and 0 would be in the middle. Okay, so here's a number line. Your value for R is going to be somewhere on this number line. If your value for R is close to +1, that means you have a strong positive correlation. Okay, strong positive. As your value for R gets closer to -1, that means you have a strong negative correlation. And as your R value gets closer to 0, that means you have no correlation. That means there's no correlation. This is sort of the scatter plot view, like way back up here, right? This would be no correlation. That would be an R value pretty close to 0. Okay. This would be an R value pretty close to -1. And this would be an R value pretty close to 1. Okay. So R is going to bounce back and forth between -1 and +1. And so everything that I just talked about is outlined here. If R is equal to 1, then there's a perfect positive linear correlation. If R is equal to -1, it's perfect negative linear correlation. And if it's equal to 0, then there's no correlation. There's no correlation. The data doesn't fit the line. It's a poor model. Don't use it. Okay. And so what we'd like to do is have our R values be very close to either +1 or -1 and far away from 0. Right? We don't want correlations close to 0. So, oh, look at this. Here's our beer data. Okay. So again, the data that we had last time, exact same example. Here's the alcohol content. Here's the calories. We're going to slap this into a spreadsheet. We're going to calculate the mean, the difference from the mean, the square of the difference from the mean. Then we're going to add them all up to get SSX. We're going to calculate the mean of the Y's. Then we're going to find the difference from the mean, the square of the difference from the mean. And then we're going to find SSY. We're going to add those all up, and then we're going to find the product. This is the exact same spreadsheet that we had in the last section. Now we're going to take SSX. So we're going to take SSXY. We're going to divide it by the square root of SSX times SSY. So you take this number, you put it here. You take this number, put it here. This number, put it here. Plug it into a magic calculator, and out pops this value. That is the correlation coefficient for our alcohol and calorie information from the beers that we looked at, okay? And this is an A-, right? It's about a 91%. That's an A-. That's a pretty strong correlation. Is it perfect? No, it's not perfect at all, but it's still pretty strong. Like anything in the 90s is a very strong correlation, okay? So now we have our linear correlation coefficient. That's great, but there's one more thing that we need. One more thing that actually is more important than R. And that number is called the causation correlation coefficient, okay? And I jumped too quick here. Wait, I got to back up just a little bit. Remember that correlation does not mean causation. Okay, and we are going to get to this other variable that I just talked about. It is called R squared. Okay, it's called R squared. And that's the number that we really want to get to. And all you have to do is take your value for R, this value here, and all you have to do is raise that value to the second power. And that will give you R squared. And that's what we really are looking for. But before we get to R squared, sorry, I spoke too soon on R squared. Remember, correlation does not mean causation. Just because two things are correlated doesn't mean that there's causation. And so here again is an example from the spurious correlations that we talked about earlier, right? This is the per capita consumption of cheese. So how much cheese people are eating in the United States. And it correlates at a 99% level with the revenue generated by golf courses. Okay, so as people eat more cheese, golf courses make more money. People eat less cheese, golf courses make less money. Now, why would this be? Anybody want to put on your tinfoil hat and guess as to why? Maybe on golf courses, they have this thing called the beer cart or the beer truck, you know, that has liquid beverages in it, and it drives around the golf courses, and people say, hey, yeah, I'd like a water or something, right? Maybe they replace the beer cart with a cheese cart, and there's a cart that drives around the golf courses with like cheese. You're like, yeah, I got some brie for you right here. I got a little mozzarella. What do you want? Hey, you got any Colby Jack? Yeah, I got Colby Jack for you. Okay, here you go. You know, maybe that's what's happening. Or here's another one. The government has put a molecule in cheese that makes you want to go outside and golf. And the golf industry is secretly paying senators to pass laws so that way this molecule can be included in the cheese. That's what it is. That's what it is. I'm sure that's the one. Okay, so you come up with one. Message me. What is your conspiracy theory as to why consumption of cheese so strongly correlates with revenue generated by golf courses? I don't know. You figure it out and let me know. And maybe we can, I don't know, maybe we can write a paper about it or something. But anyway, remember, correlation does not mean causation. Okay. And we give you a couple of examples here again of some sort of spurious correlations. But now let's get into the final thing in this chapter. Okay. The final thing. And this is called the coefficient of determination. This is what we're really looking for. This is the end, right? R squared. So in order to find R squared, all you do is you square R. It's pretty easy. But this is the number that really does the trick to explain how much of the variation is explained by the correlation between the two versus the total variation, okay? And all you have to do is square R. So mathematically, it's a pretty simple thing to do. And we're going to show you how to do this in Google Sheets. So you don't have to do any of this by hand. If you want to do it by hand, you know what the formula is. You can go up here, and right there's the formula if you want to do this by hand. But we're going to show you how to do this in Google Sheets using two formulas. So it'll be pretty simple, okay? So again, we're going to go down here, and here is our information from the beer data. Remember the alcohol content and the calories. And so we have, once again, our SSX, we have SSY, we have SSXY. We plug them in and we find R, which is this value right here. And then we just take that number and we square it. And this is R squared. So that is about 83.4%, which is a solid B. Okay. So what this means is that of the variation between the alcohol content and the calories of our 9 beers, 83.44% of it can be explained, of that variation can be explained by the relationship between those two variables. So those two variables constitute 83.4% of the explained variation, okay? What's left over? The 16.56. Remember, you got that by saying 100 minus 83.44. The leftover variation is the unexplained variation. And this is due to other factors. So for example, sugar. How much sugar is in the beer? The type of yeast that is used, or maybe other ingredients that were put into the beer. So it's not necessarily alcohol content that causes the calories. There's other stuff in there as well. How much does that other stuff impact the total variation? 16.56%. How much of the variation is explained by the alcohol content and the calories? 83%. Okay. So this is kind of the measurement. This R squared is the measurement that we're really looking for, and it separates out what we can explain and what we can't explain. Okay. And so when you do data analysis on this, a very good coefficient of determination has a very small unexplained part. Okay. And so here's how you use technology to find R and R squared. So again, we're using our data from the beer information, but here are the two formulas. So to find R, the formula is equals correlation, right? CORREL. And once again, you put in your Y data first, and then a comma, and then your X data. In order to find R squared, the formula is RSQ, R squared. And again, you put your Y data in first and then your X data. Okay. And so here's the information from our beer data. Here's the scatter plot from our beer data. Here is where you go into Google Sheets and you go to the chart editor customize tab, and you're going to check this box right here that says show R squared. And what that will do is next to your Y equals MX plus B formula, it will calculate R squared and put that value right in there. Now, what if the problem is asking for R? Well, you just take the square root of that number and that'll give you R, right? If R squared is 0.834, then R is the square root of 0.834, okay? And again, that is the correlation coefficient, which is R, and the coefficient of determination, which is R squared. And so here is my data, X and Y. So to find R, I'm just going to type equals CORREL, and then a parenthesis. Highlight the Y data, comma, highlight the X data, enter, and there is your correlation coefficient, -0.76, okay? To find R squared, all we got to do is take this value and square it, raise it to the second power. And so all I did is I typed in B14 and then Shift-6 to get the caret, and then the 2 to square it. And so that's how you can find R squared indirectly. Okay, we'll show you how to find it directly in a little bit. And remember, we're recording this, so if you want to go back and see what key did he hit and how did he do that, you can go back and watch the recording. Okay, let's do R squared. So in this case, we're going to say equals RSQ. That's the formula for R squared, RSQ, parenthesis, highlight the Y data, comma, highlight the X data. Hit enter, and there's the value of R squared. And notice it's the same value that we had when we calculated it indirectly by squaring R. Now let's go to R, and we're going to do SQRT. We're going to take the square root of this value, and you'll see that it's exactly the same as this one. But there is a slight difference. You notice that this value is positive and this value is negative. So if you decide to find R indirectly by square rooting the R squared, remember when you square root a number, there are actually two answers. There's a positive answer and a negative answer. So if you go back to, like, I don't know, probably 6th grade, where you learned about imaginary numbers, if you have the square root of 25, you may think the answer is 5, but actually there's a second answer, which is -5, okay? And when you use technology, technology always gives you the positive answer. This is called the principal root. And technology kind of ignores that -5. Well, in this case, you can't ignore that -5. You have to keep in mind that the square root of a number can be positive or it can be negative. And so how do you determine, when we go back to this and you were taking the square root, how do we know if R is positive or negative? Take a look at the slope of the line. If the slope of the line is negative, which in this case it is, see that line right there? Negative slope. So that means this R value has to be negative. So if your slope is negative, your value for R is negative. R squared will always be positive. R squared is always positive, but R can be positive or negative. Okay, so this is problem number 9. what should we do? Let's copy and paste this data into a spreadsheet. How's that sound? So I'm going to highlight this table, copy it, and go over here and paste it into Google Sheets. And resize it a little bit. So there is my data, okay? Let's do this one directly, okay? No fancy graph and lines and all that. Let's just get right to the answer. So let's find R, okay? So that is equals CORREL, parenthesis, highlight your Y data, enter a comma, highlight your X data. There you are. There's R. Done. Okay, we're going to copy that and we're going to paste it over here. There's R. Now, what you may notice is there's an outlier in this data set. Okay, so this is the correlation with the outlier included, all of our data points. We need to remove the outlier and calculate R again. So taking a look at this data set, can you identify the outlier? I think it's this point right here. I think it's in row 16. I think that's my outlier. So I'm going to highlight that outlier and push delete on my keyboard. Boop. And the outlier is gone and my value for R changed. Do you see that? There's the outlier without outlier, with outlier, without outlier, with outlier, without outlier. Changes quite significantly. We'll copy that. We'll paste it here. Okay. So now I gotta round this, don't I? What do I gotta round it to? Does it say? It doesn't say. We'll leave it all in there anyway. But does the outlier significantly influence the value for R? Oh, yes, it does. Yeah. Including the outlier changes the evidence regarding the linear correlation. Oh, yeah, 100%. 100%. This is the linear correlation with the outlier. This is the linear correlation without the outlier. Huge influence. You went from a 91 to a 1%. That's a pretty big drop, right? You took an exam, you got 91% on it, and then someone says, oh, I forgot to grade this one question, and they grade it and you drop to a 1%, right? Yes, this outlier very much changes it. So if we hit submit, I think we're good to go, okay? Now, if you wanted to see this for real, you would highlight this data set. Oh, I got to put the outlier back in. So let's put that back in. There it is. I'd highlight this. And if you wanted to see it, if you're a visual person, and I am a visual person, so I would do this and I'd say insert chart. Dun, da, da, da. There's my scatter plot. And boy, you can see that outlier clear as day, right? There he is right there in the upper right-hand corner. There's the outlier. So we're going to go to series. We're going to scroll down to trend line. We'll make it red so we can see it a little bit better. And then we're going to go to label. We're going to say use equation, and then we're going to click this button, this checkbox that says show R squared. Now it doesn't give us R, but it does give us R squared. So there is the value for R squared, 0.846. So I would take the square root of that number, and that would be R with the outlier. And then I'm going to take the outlier away. Ready? So we'll take the outlier away. Holy cow, look at that. Now, it's hard to see exactly what happens because the whole graph changes, right? The X and Y axis rescale. But look at the slope. The slope on this line is 125. The slope on the line is 125. When I remove the outlier, the slope goes to 2.19. See the number in front of the X? 2.19. Here's with the outlier, a slope of 125. And without the outlier, a slope of 2. So your slope goes from 125 down to 2, depending on whether or not you include the outlier. Significant difference? Oh yeah, big significant difference. All right, cool.